Hey, and welcome. Ever just look around and wonder what everything is actually made of? I mean, everything. The phone in your hand, the air you're breathing, all of it. Well, today we're going to pull back the curtain and look at the secret rules that run the entire show. We're diving deep into the building blocks of our universe. All right, so let's start with a bit of a riddle. What on earth could the invisible air right here in this room and a giant blazing star millions of miles away possibly have in common? I mean, they seem like total opposites, right? But believe it or not, they share one fundamental secret. And the answer is they're both made of matter. Now, the official definition is pretty simple. If it takes up space and has mass, it's matter. But the really mind-blowing part is that this means everything, from a tiny grain of sand to the biggest star you can imagine, is all built from the exact same stuff. But for the longest time, people had no idea. Scientists and philosophers, they argued about it for centuries. One side thought matter was continuous, like a solid, unbroken block of wood. The other side was convinced it was made of tiny, separate little bits, kind of like a pile of sand. Well, turns out Team Sand was right. Everything is made of these unbelievably tiny particles, way too small for us to ever see. So, let's zoom way in and uncover the secret life of these particles. We're about to find out the hidden rules that govern pretty much everything. And what's so cool is that the behavior of all matter, literally all of it, boils down to just three simple rules that these particles follow. 1, there's space between them. 2, they're always moving. And 3, they pull towards each other. That's it. So let's break them down one by one. Okay, first up, particles have spaces between them. Now, that might sound a little weird, right? I mean, how can a solid table have empty space in it? It feels solid. Well, there's a really simple little experiment that proves it. So, picture this. You take a glass of water and you carefully mark the water level. Then, you stir in a spoonful of salt until it's totally dissolved. Logically, you'd think the water level would go up, right? But here's the crazy part. It doesn't. This is like a magic trick that shows the salt particles are actually slipping into the empty spaces that were already there between the water particles. Wild. Now for rule number 2, and this is where things get even more interesting. Particles are never still. Ever. They are in constant, jittery, random motion. And this built-in movement is something scientists call kinetic energy. And this explains something you've definitely experienced. Think about it. Why can you smell hot food sizzling on a stove from clear across the room, but for cold food, you have to get right up next to it to smell anything? It all comes down to how fast those particles are zipping around. See, the little scent particles from that hot food are packed with energy. They're moving super fast, mixing with the air particles, and traveling all the way to your nose. That whole mixing process is called diffusion. And when you add heat, you give the particles way more kinetic energy, they move even faster, and so diffusion happens a whole lot quicker. And our last rule. This is basically the glue that holds the universe together. Particles attract each other. There's this constant force pulling them towards one another, keeping them from just flying off in every direction. The strength of that pull, though, can change a lot. The source material for this gave us this fantastic analogy. Think of these Idumishmi dancers. Sometimes they're holding on super tight, locking arms, almost impossible to pull apart. Other times, maybe they're just holding hands loosely. That force of attraction between particles works just like that. Sometimes it's incredibly strong, other times it's pretty weak. And that difference is everything. Okay, so there you have it, our 3 fundamental rules. Particles have space, they're always moving, and they attract each other. All right, enough with the theory. Let's put these rules to work and see how they create the actual world we live in, the world of solids, liquids, and gases. This is where it all clicks into place. So just look at the solid column. Here, that attraction force is super strong, and there's barely any space between particles. They're locked in, just vibrating on the spot. Okay, now slide over to liquid. The attraction is weaker, which gives the particles enough wiggle room to slide past each other. That's why liquids take the shape of whatever container they're in. And finally, in a gas, the attraction is almost zero, and there's tons of space. The particles are just rocketing around randomly, which is why a gas will expand to fill any room and is so easy to compress. So the whole secret is this. The only difference between a solid block of ice, a glass of water, and a cloud of steam is just the balance between the space, the motion, and the attraction of their particles. And get this, the very same water molecule can be in an ice cube 1 minute and a cloud the next. The only thing that changes is how much energy it has. That's the key. And of course, these states aren't set in stone.
We can force matter to change from one state to another, and we usually do it by messing with the temperature or the pressure. Let's take a look at how that actually works on a particle level.
Okay, here's a neat little scientific mystery for you. If you take a beaker of melting ice and stick a thermometer in it, the temperature will stay locked at exactly 0 degrees Celsius until every last sliver of ice is melted. Now, you're pumping heat into it the whole time, so where's all that energy going? Why isn't the temperature rising?
The answer is something called latent heat. Latent literally means hidden. So this energy isn't making the particles move faster, which is what temperature measures. No, this hidden energy is being used for one specific job: breaking the bonds, overcoming those forces of attraction that are holding the particles in that rigid ice structure. It's the energy you have to pay to change state. And this is not just some abstract concept. It has some very real and kind of painful consequences. As our source material points out, because of all that extra hidden heat it absorbed to become a gas, particles in steam at 100 degrees Celsius have more energy than particles in boiling water at the same temperature. That hidden energy is exactly why a steam burn is so much more severe than a burn from boiling water. All right, let's bring all this science back home and talk about a process where all these particle physics ideas are at play every single day: the cooling magic of evaporation. You know how a puddle on the street eventually disappears, or how wet clothes on a line get dry? That's evaporation. And it's different from boiling because it can happen at pretty much any temperature. And here's the other key difference. It only happens at the surface of the liquid, where a few super energetic particles manage to break free from the others and escape into the air. And once you know that, it totally explains how to get your laundry to dry faster, right? You spread the clothes out to increase the surface area. A sunny day adds heat, giving more particles the energy to escape. A windy day blows those escaped particles away, making room for more. And it works best on a dry day because the air isn't already saturated with water vapor. It's all just particle physics. But here's the coolest part. Literally, evaporation causes cooling. Think about it. Only the particles with the most energy, the hottest ones at the surface, have enough oomph to escape. And when they leave, they take their heat energy with them. This leaves the slower, cooler particles behind. So the average energy of the liquid that's left drops, and its temperature goes down. Which brings us to our final question, and now you have all the tools to answer it. Knowing everything we've just covered about absorption, surface area, and evaporative cooling, you can now explain exactly why wearing cotton clothes on a hot day really does help keep you cool. The answer is right there, in The Secret Life of Particles. Thanks for digging into this with me.